Hi, this is going to be a quick review of the basic continuous random variables. Any random variable will have a cumulative distribution function. Cumulative distribution function. People abbreviate this sometimes as CDF. Okay, and this is just the f of x is just the probability that the random variable x is smaller than or equal to little x. Okay, so my random variable is this capital X and little x is a fixed real number. And so this function is non-negative clearly. It's non-decreasing, which is just the monotonicity of these events. It has a limit of 0 on the left and a limit of 1 on the right, and it's right continuous. Every random variable has that. For a discrete random variable, we didn't really look at the distribution function because it's much nicer and easier to work with the mass function. But for a continuous random variable, there is no other way than really to look at the distribution function and the density that's related to it. So the definition of a continuous random variable, x has an absolutely continuous distribution, and people sometimes just don't say continuous, and I sometimes just don't say absolutely, and I often will not say absolutely. So it has a continuous distribution if the following is true: if there is a density or probability density function some people forget about probability and some people forget about function and just say density, and some people will say PDF for probability density function, little f, such that for every x, well, let's use a, for every a real number, the distribution function at a is written as the integral from negative infinity to a of f of x dx. Okay, so if the distribution function is the integral of some density, then we say that we have an absolutely continuous distribution, or just a continuous random variable, if you wish. Okay, it follows that for all subsets A of R, and here I'm gonna put a little remark, a little star, we have that the probability that x is in A is the integral over A of the density. Now the remark is that it's actually not going to be all sets, it's only going to be those sets which are measurable with respect to the Borel sigma algebra. Now you don't need to understand any of this yet. We are going to go through this later in the unit. But essentially any set you can reasonably come up with will have this property. Okay, so you have to work very hard to find a set for which this is possibly not true. So this is equivalent actually. This definition here is equivalent to having a continuous distribution. All right, if you want to find the mean and variance, then you probably want to find moments of a continuous distribution. So the expected value of x to the n, if this exists, is going to be the integral from minus infinity to infinity of x to the n times the density, if this thing exists. So when n is odd, then this thing might fail to exist. If n is even, then this thing always exists, but it could be infinite. And again, the expectation is just the integral of x times density. Again, there are cases. It could be a finite mean, it could be of infinite mean, it could be of negative infinite mean, and it could be the case that the mean doesn't exist. If both the positive ends and the negative ends of this integral are both infinite, then we just say that the expectation doesn't exist. And then the variance, of course, is, as before, the second moment minus the square of the first moment, or equivalently is the expectation of x minus mean squared, assuming that it's the mean exists, and assuming the mean is finite actually, is the expectation of x minus mean square. These two are equivalent. In order to find this, you need to know how to do the expectation of a more complicated function, and the way to do that is, of course, that take the expectation of any function of your random variable. This actually needs to be some reasonable function, measurable function, g of x times f of x dx, assuming that this integral exists, and then if you just plug in x minus mean squared for g, then you know how to calculate this one. Okay, so that's the general kind of framework of continuous random variables. And next I want to very briefly go through a couple of well-known continuous distributions which you all have seen in your first probability course. So examples, the uniform parameter alpha and beta distribution is a distribution. Let me plot the density. So the density, so we are talking about continuous distribution, so all of these guys will have a density. And it looks like 0 here, it's some value there, and it's 0 there. Now if you go back to the continuous random variable definition, then you find that if you take the limit as a goes to infinity of fa, by definition this has to be 1. On the other hand, it's going to be the infinite integral of the density. So density function, probability density function will always integrate up to 1 for a proper random variable. And so this thing has to integrate up to 1, which means that this height has to be 1 over beta minus alpha, this height here. If you want, you can actually formulate this. You can write up some nice formulas saying it's 0 outside alpha beta and this at between alpha beta. I'm not going to do this here. Okay? And what if you want to plot the distribution function? The distribution function is just the integral of this guy. So it's going to be 0 here. It's going to be a linear increase. So that's the distribution function. It's going to be a linear increase from here to there. The slope of this curve is 1 over beta minus alpha, and we're going beta minus alpha distance, so we end up at height 1, and it continues at height 1. Okay. The point with uniform is that if A is a measurable set, you don't need to understand what that means yet. If A is a reasonable set, then the probability that x is in A is going to be the total length of A, or if you want the Lebesgue measure of A, compared to the total length of your interval. So for uniforms, it's always comparing lengths, or comparing, you can actually generalize this to multiple dimensions, then it's comparing areas or volumes. That's why we like the uniform. That's one of the reasons. The expectation of uniform is very easy. It's just the midpoint of the interval, alpha plus beta over 2. And the variance of the uniform is not difficult either. It's beta minus alpha square over 12. And actually, if you know your probability, and if you know a little bit of, think about translations, then it's not hard to see that the variance must be proportional to beta minus alpha square. The number 12 is something you have to work for a little bit more. Okay, so this was the uniform random variable. The next one I want to show you is the exponential of parameter lambda. I forgot to tell you, but I think it's clear from this picture that alpha and beta are two real numbers. Alpha smaller than beta. Okay, so exponential lambda. Lambda is a positive real number. Real. Alright, so the density of this guy is lambda e to the minus lambda x when x is positive and 0 when x is negative. I didn't tell you what the density is at 0, and I don't care either. The density is always to be integrated. At a single point, its value doesn't matter. So if I don't define it at 0, it doesn't matter. And if you integrate this out, the distribution function is going to be 1 minus e to the minus lambda x for positives and 0 for negatives. Here I did tell you what it is at 0. Of course, right continuity will just tell that. Anyway, these values actually agree at 0. Alright, and the expectation of x is 1 over lambda, and the variance of x is 1 over lambda square. And one of the main reasons why we like the exponential is that it's memoryless. It has the lack of memory property or memoryless property. For every t and s positive, fixed, not random of course, we have that the probability x is larger than t plus s given it's larger than t is the same as the probability that x is larger than s. And if you want to plot this, then you would say that, think about this as time, a random time interval. This is 0 and this is x. And then if you have time t here, deterministic time t here, and somebody comes and tells you that x survived at least this much, then the remaining time is again exponential lambda conditioned on the event that x is larger than t. So if x is larger than t, then the probability it's further larger than another s is the same as if it was born new. Okay, that's the memoryless property. Notice that it's a conditional probability. It's not saying that this distance is exponential, it's saying that this distance conditioned on x being larger than t is exponential. Okay, so that's the exponential random variable, and the last one is of course the normal. So why do we like the normal random variable? We like it because of the central limit theorem. It is going to be the limit of a rescaled sum of IID random variables. Normal of parameters mu and sigma square, where mu is a real number and sigma is usually a positive number. So this will have density 1 over root 2 pi times sigma e to the minus x minus mu squared over 2 sigma square. That this is a density is something I'm going to show you in the next video. And so the reason we like it is that if you add, let me just state the central limit theorem. This stands for central limit theorem. We're going to prove this towards the end of the unit. It says that if xi are IID with mean exi equals to mu and variance xi equals to sigma square, both finite, then if you do the sum of the first n and you subtract the mean of the first n and you divide by standard deviation of the first n, this will converge in some sense, namely the probability this is more than or equal to a fixed number a converges as n goes to infinity to phi of a, which is the integral from minus infinity to infinity, to a of the standard normal density, 1 over root 2 pi e to the minus x squared over 2. Okay? That's why we like the normal. No matter what you add up, if it's a finite variance and they are independent, then in this scaling everything converges to normal. We're going to prove this towards the end of the unit. Okay, and a couple of more remarks here. What you see on the right hand side is phi, the standard normal distribution function. Okay, and that's the definition of it, where inside here you see the standard normal density. And what is standard normal? So what I abbreviated standard normal is just normal of parameters 0 and 1. 0 for mu and 1 for sigma square. Okay, what is the okay, so one more important and very nice property of normals. If you take x a general normal, mu and sigma square, so that's an abbreviation for saying that x is normal with parameters mu and sigma square. If x is normal mu and sigma square, then ax plus b is again normal with parameters a mu plus b and variance a square of sigma square. That the mean is this and the variance, if that is not very difficult, of course, just generic properties of mean and variance. That the thing is still normal is a not completely trivial fact. You can check that by doing the transformation of normals. From this it follows that if you subtract the mean and divide by standard deviation from a normal random variable, it becomes standard normal with mean 0 and variance 1. It's also not very hard to see that the expectation of a normal is mu and the variance of a normal is the parameter sigma square. Okay, so these are the main properties of normals, and this transformation property is very nice because now if you want to find out about the probability that x is smaller than or equal to little x, then what you can do is write this combination of x. Sigma is always positive, so I can divide with it without changing the inequality. And now you can say that this guy here is standard, and straight away you get the distribution function of standard normal, which is phi at little x minus mu over sigma. The distribution function phi has a nice property which you can just find out from the nice bell curve of the standard normal distribution function, namely phi at negative is 1 minus phi at positive for every real z. These are all things you have most likely seen before, so I'm not going to spend much time on them. The only thing I'm going to do in the next video is to prove that this is actually a distribution function, because that's kind of nice, and I'm not sure if you've seen that before.